First, I would like to thank the committee that is organizing this CEGRAPI, and mainly the committee for the workshop for industry applications, because they invited me here, and Microsoft in the United States, but all my education was done in Brazil, financed by CAPES and PQ and the Brazilian taxpayers, so thank you. And of course, Microsoft, because they are paying my tickets, and family and friends. And before I forget, what you see today is not only my work, it is the work of a lot of people that work inside Microsoft, Microsoft Research, and several other organizations. So thank you to all of them. And this is part of the workshop in industry applications. So as someone who was invited here, I used some time to take a look at the papers that will be presented later today. And one of the very important things, if you really want to connect the academic knowledge with the industry, is to see where the industry is going. So if you look at the papers, you see that they have a lot of subjects that are very different. And the tendency of you, when you are young and when you are kind of trying to still decide what is that I will learn, is to think two things. Both are wrong. One, it is that you have to understand everything. First, that is impossible, and so you will be always disappointed with yourself and unhappy, and nobody wants to work with unhappy people. At least I don't. So, and the second thing, it is to think that what is important today will be important tomorrow. So that is another way to fail in the industry, because I was in the organizing committee for this same event when it was in Caxambu 15 years ago, I believe. And at that time, everybody was talking about corals, about things that today totally different. So don't be worried if you don't understand everything, and try to really learn from what the industry is doing today, but keep an eye on the future. So obviously, you didn't come here because of my name. You came here because of Microsoft. Microsoft is the largest software company in the industry. So that you know what is that we represent, Microsoft made $54 billion selling software last year. The second place was IBM, who made $22 billion selling software. And you have this list, but the important thing to look at it is where are our major competitors. Apple, which is definitely one major competitor today, they made $1 billion and $300 million last year selling software. It is only 1.8% of their revenue. Intel made 751, and Google made $500 million. That's almost a rounding difference in our revenue. So this is data that you can get from the internet. There is a site, Software Top 100, and the first Brazilian company that shows up in this is this company called TOTVS that made $478 million. So the software industry really needs to grow in Brazil. And for the same reason in all of Latin America, and even in other countries. It cannot continue to be 50% paid by the American consumer. So we know that software is used everywhere, but today there is this huge mismatch. 50% of the revenue of any major company comes from the United States. So let's deal with the theory. All the theory of my presentation was presented earlier today. So if you have seen that presentation, everything that we will present in terms of academic knowledge was presented there. So let's go straight to the conclusions. The conclusions of my presentation are: doing software for a living takes less than 10% of your time. It is less than 10% coding. Also, software, for you to be successful, you have to know something more than just to do software. As it was said by Professor Silvio, I am more successful because of the knowledge that I have of physics than because of the knowledge that I have of computer science. And the other thing is that developing software teams is extremely hard. Far harder than developing software itself. So, since we know already the conclusions, anybody has questions? Any questions before we go through a pointless presentation? Okay, you are shy, so let me talk to you a little bit about me. Okay, I am described by the person that knows me the most, who is my wife, as the perfect combination of Will Smith and Mr. Bean. And probably more like Mr. Bean. And if you have ever seen a movie from Mr. Bean where that picture plays a very important role, that's why I took this picture with the picture, the Whistler's mother. And basically what my wife says is, I'm this person that is going through life and through a lot of situations, and everybody else is in panic, and I'm there, calm, and just like the accidents are happening all around me, all over, and I go straight, and when I look, why is everybody late? And that is the best description. But there is one thing about me that really probably helped to explain why sometimes I succeed where others fail. It is, I'm very practical. So a lot of people say, oh, I know a lot about image processing. I can do a lot of segmentation. I can do a lot of picture matching and everything. The thing is, my wife calls me and says, yeah, Alisson, I was taking this picture of our daughter many years ago with her teacher, and this other girl comes around and disturbs our picture. And I said, okay, I will try to remove it later with segmentation, grab cut, and all those things. And just to show her how things will look afterward, I get Microsoft Paint and do this lousy job of removing the girl. And yet, for many years, this picture was hanging on my walls, even though it's obvious that it is a lousy job here. I cut the thing midway through, I did it in 5 minutes, and my wife was, oh my. This is how my wife explains, my husband really knows image processing. Can you imagine this? For all the time I spent studying, this is how people really understand what you do. So I've been at Microsoft for 13 years. For the first 8, I couldn't explain my mother what I did, because I did software like BizTalk, software like the business framework, and a lot of things that most people like you will never hear of, and you are not missing anything. The key point was when I finally started to work with image processing, which was when I started working Microsoft Office and working Excel doing data visualization. Then I went to work in England with Team Microsoft Research, doing the tech transfer from research to development. So that was a key time. I did a software that I definitely recommend that you take a look at. It's called Microsoft Research Auto Collage. It makes a collage of several pictures to summarize that set of pictures. And then I came back to Redmond. I was working for 1.5 years in a team called Engineering Excellence, which is the team of people inside Microsoft that teach new developers how to work at Microsoft. And that was a very good experience because both in Microsoft Research and in Engineering Excellence, I could really have a little more impact in software teams. And also work with software that I could explain to friends and with hardware. When I was within Microsoft Research, I was in the incubation for this project that later became the Microsoft Touch Mouse, which allows you to do gestures over the mouse. It's a very interesting project, and it's very cool when you go to a country like China and you can see your product being sold. Something similar to what is happening with the Kinect. And I can tell you a lot about how software works inside companies, the politics, psychology of developers and other things, but I shouldn't, because if you remember the Wizard of Oz, you should only talk about things that you have a diploma about. You have a diploma for that, you can talk about it. Everybody has brains, they can think by themselves. You should only talk about things if you have a diploma. So I only have diplomas in physics and computer science. So that restricts the subjects I can talk about. You are living right now through two huge transformations of these subjects in history. Physics is going through the theory unification, and I will not bore you with details for long. And if you have heard of this thing called string theory, it is the huge topic of physics today. I can talk only about that if people will allow me to change the subject. And the cool thing is that is done through a lot of collaboration among several universities, and it is resulting in a lot of publications. On the other side, you can see computer science and software development is going through a similar transformation within your lifetime. One is called this natural user interface. And I don't know who came up with this name because it is a terrible name. Computers don't show up in nature. So natural user interface is a misnomer. However, this is a fight that is happening right now and where the Kinect really touches this presentation. There is another one that you should definitely learn, cloud computing. In a few years, this topic of you storing data at your house, it will be totally obsolete. You cannot do that. You don't have a power plant in your house. If the electricity goes down, you are down anyway, so there is no point on storing data at your house. And I don't really care if you are storing your data in Amazon, Google, whatever, but for image processing, mainly for image processing, that is the future. And it is something that you need to learn. I will not talk about this any longer. Let's focus on the natural user interface. If you remember what I told you about physics, the problem is in computer science, this change in history is happening in a totally different way. It is happening through competition. It is happening through patents. Companies are investing a lot of money, companies like Microsoft, Apple, Google, and creating patents about every single subject in this area. Who has a patent here? 1, 2, 3. So how many patents you have? 1, 2, 2. I have 10. So it cannot continue to be this way, that one single person, because leaves the country, has far more patents than everybody else in a room with all such talent. So I cannot also, of course, solve that problem. The problem that we have to solve is, in the future, our children will not understand the computer as we know it. I don't know how many of you have children, but I have two. I have one that is 13 years old and one that is 8 years old. They don't understand those devices. I understand. but they absolutely don't understand how they work, why they would exist. That is the most important thing. They don't understand why music would not come directly to my iPod. Why? Really? Can you explain this to my 8 years old? Because I cannot. Why would somebody leave their homes, go to a place, buy a disc, strange and large, put in this device, and hear a lot of noise that is not part of the music? Forget that she doesn't know how the thing works. Why is the question here. Same thing, tape recorder. Folks, it is serious because you are living in countries where these things still exist for you to see. One of my interns at Microsoft, we asked him to go and get a diskette. A diskette, do you know a diskette? He didn't know what that was. He never saw one. He went to a major university in the United States. These things do not exist any longer. For many years there. There is no way to start a conversation about a topic that these people never saw. So the thing is, that is where the kinetic, that we will not be talking about the kinetic in 20 years. It is really something new. This is, I'm here because I will briefly try to describe how we are participating in this industry of the natural user interface. It is the work of a lot of people. The kinetic for Windows using Steam within Microsoft has 90 people. A Microsoft employee in the United States costs on average $200,000 per year. So this is an investment of $18 million only with the employees in the United States. Plus, we have 25 people in China, where it is right now still cheaper to have it to be technical. So this is the way the industry works. And of course, not all kinetic efforts are related to us. Okay, we have nothing to do with the kinetic control. So, what is that my team does? If you paid attention to the diagram, there are 12 people working in the computer vision subsystem for the kinetic for Windows. So what is our task? The kinetic already existed. This is a device that was created for the Xbox. And this device is really an achievement for computer vision. I will show a demo, but I believe most of you have seen how the kinetic works. And the real breakthrough is computer vision. It is a breakthrough that allows a device attached to your computer to see a person in front of the computer and allow the programmer to really code knowing that there is a person there. The people that created the software, the kinetic skeletal tracking, they won a prize even within Microsoft because it is an achievement. And it is a special achievement because of the Brazilian that was behind this, pushing the team to finish it. He won an individual award, and Alex really bet his career on connecting all these people from different places of the organization to create the skeletal tracking for the kinetic. For a long time, people believed this is a problem that we cannot solve. And he managed to convince a lot of people to do this. And it shows that you need to learn more than technology. Who knows what is that his father does? His father is the Brazilian ambassador to Switzerland. So you need to know how to really convince and connect people. It's far more important than just the technology. So, the Kinetic for the Xbox is done. It is the best-selling device in history. What is that my team is tasked with doing? There is this small problem. The Xbox, it is a Power PC CPU. And we have to migrate this for Windows, where we have an Intel or AMD CPU. The Xbox has a known bus internally. It has a USB connect doing externally, but for all purposes, we can consider it is a known bus that will always be there. Here we have USB connections, and USB standard, I don't know if you ever coded at that level, is a terrible standard, but let's go over this. The Xbox will support exactly one device per machine. In Windows, we support several devices per machine. It is limited by how many controllers you have. The Xbox has a known architecture. Windows, we have this eternal problem of having 32-bit and 64-bit, and someday even more. The Xbox has a known GPU, a graphical processor, and for Windows, we were asked not to have a GPU dependence. So remove the GPU dependence because we cannot guarantee that every Windows machine will have a GPU. The Xbox has a selected audience, people that are developing games, and here we have a general audience with unaltered scenarios. So let's see how we did. But before that, any questions so far? You don't have to pay to make questions. Okay, let's see how we did. So I will use this application called Kinetic Explorer, okay? So this is how we did. We got this code, we migrated this code, and basically we managed to be able to, in any Windows environment, return to you the skeleton of a person in front of you. And of course, it doesn't know that I am back or forth. There are some constraints, but most of the time, see, within the range of the device, it returns successfully. There is a confidence associated with each joint. We return 20 joints. There is a lag here because of the software that is running in the demo, and this is a 3-year-old computer. It is a very good computer. It's a MacBook Pro, but it is 3 years old. So if I do this, it finds. So this is reasonably good, isn't it? So we are doing 30 times per second. So every 33 milliseconds, we have to return to you this skeleton. Of course, if we took 33 milliseconds, you would have nothing, no time left for you to do anything. So we return this data to you within 15 milliseconds. So that is the challenge. In any PC that is a reasonable PC, we return this data to you in 15 milliseconds. And this allows you to do a lot of things. So the Xbox, the device, this device is giving me the color, that is a color camera, you probably heard about this, and the depth. And our subsystem is finding for you the skeleton. This allows you, and I will have to close this application here, but this allows you to do things like, and we ship a lot of samples with our application. Let me, oh, here. Okay. This allows you to do things like let me just show 2 samples. Using, for example, only depth and the information about color, you can do already some very interesting things. So, for example, using only depth and the color information, I can do something like green screening. Okay? So sorry, but basically this is very easy to do. If I know what is background is what is foreground, I can do this easily. Okay. This presentation counts as my exercise today. So another thing that you can do is you can do a small game. We even show you the source code for these games. And oh, let me close here. So wait a minute, let me put the game here. So you can do games where you touch things, okay? And basically you as a developer, you can do a lot of things. Oh, what? So, and the other thing that you can do, it is you can try to do a more natural user interface. So if you are doing nowadays a slideshow, most times you have to control using controllers, but the idea here is you are the controller. So if you are in front of the device and you make a gesture, I can just say, okay, just go to next. Okay? So that is the idea. And why can I do this and I cannot do this to return? Which is a migration. You will always have to go back with your arm. But basically you can do this and then you just use the other arm. Okay? So I have more demos, but we don't have time for everything. Just one more. And again, the Xbox also has a very cool concept of, it has a sound array, so it knows which direction sound is coming from. So you can do games in which a person here is talking something and it can differentiate a person from another person. But the other thing that we also ship is we ship a face tracking SDK that focuses not only on your skeleton, but in your face. So it finds your face, and then it gives you the information of where are the parts for your face, so that you can create an application that, I don't know, it will control Mickey Mouse or something. Okay? So, okay. Back from the demos. Okay, any questions? No questions related to them, please?
What is the support distance of the device?
We will talk about that. But the support about it is from 80 centimeters to 4 meters for the device that is sold for the Xbox. For this device here for Windows is from 40 centimeters to 4 meters. Okay, so the question was the distance that it supports that information.
The device is different. It is different.
The device is different. The device for the Xbox is different from the device for Windows, yes.
And despite this limitation of distance, what else is different between them?
There are a lot of technical differences that, of course, we cannot talk about publicly. But basically, there are two major differences. There are the technical differences inside the device that we cannot explain to you publicly, and there is the licensing difference. Basically, the device for the Xbox is sold for games at your house. You are not supposed to use it for commercial applications, and this device is licensed for commercial applications because it is officially supported by Microsoft for this kind of environment. So that is the major difference. Any other questions before we go deeper into how the software works and does this thing for you? Okay. Oh, please.
Do you have any application in which you manipulate 3D objects, so rotate, zoom, a virtual 3D object?
Okay, the question is if we have any applications. Our goal at Microsoft is not to do the applications.
I mean, some example like that, in order to understand if you have enough accuracy for manipulating a 3D model. Zooming and rotating instead of
Zooming and rotating.
Similar to the image that you have presented.
Exactly. So we don't ship such application that showcases how people can zoom and do other things. I will talk about this in the future, but I believe most of you may have seen this video here, but let me show you what other people have seen.
Sensor that turn voice and movement into magic.
Xbox. But
We thought this would be fun to play with.
Be careful, because some things here are just visionary, they are not real yet. But some are real, and I will clearly identify for you. This you can do. This you can do. Really, just consider your hand.
Unexpected things.
This you cannot. But the magical thing you can. This you can do.
Beautiful things.
And all those things you can do. And this you can do. If that is real. That is a hospital in Seattle where kids are using it for physiotherapy.
Which is why, even though the world keeps asking us what we'll do next, we're just as excited to ask the world the same thing.
Okay, so basically, our goal is that the market will do the applications and we enable the applications through the software development kit. But again, there are several examples. Some I'll talk a little bit more than others. Okay? Okay, so what is that we really do? So if you imagine software, the way that we typically represent software is we do block diagrams, isn't it? We do a lot of these block diagrams as if connecting the block diagrams would make the software work. And the funny thing is, sometimes it works. Kinetic has internally some subsystems. I work for the computer vision team that today does the skeletal tracking. There is another dev lead for the runtime and for the drivers. We have a lot of people working on this toolkit that I'm showing you that has the examples in C#, C++, in Visual Basic. And of course, the market is developing applications. I'll not go deep into this because I don't want to explain this thing of Microsoft has what we call native code and managed code. I don't want to go into this technical detail in the presentation. But the most important thing is to understand what is the role of each part of that diagram. The drivers are really a very hard part. They are getting the data from this device and through the USB getting this into the computer as 3 devices. Indeed, if you connect the Xbox One, it will be 4, because it is different already. It has the audio array, it has the camera, and it has the depth information. And this device has the security control, because, as I said, they are different. Again, I can go forever into the drivers, but let's focus on the image processing. The Kinetic is basically a camera, the RGB camera, the infrared laser that is then dispersed through lens, and then the infrared sensor, and the microphone array. Why infrared, we will see soon. Let me just finish with what is that the runtime does. The runtime subsystem, what they do is, they do a lot of software to keep running and see if there is a sensor connected, if it is initialized properly, and so on. Then they get the data from the drivers and make it available to applications or for the skeletal tracking, and call skeletal tracking when you enable skeletal tracking. And the emphasis for the runtime is getting this data out of this device as quickly as possible. Remember, we are running in a PC that has other applications running also at the same time. We should free up time for those applications. We should not use the entire CPU for ourselves. So this is just a dual-core old machine, and we are kind of very low profile with all the drivers and the runtime running here. Okay, cool. And it supports virtual sensors, test tools, and later I will describe this thing of kinetic speed. And then there is the toolkit. The goal of our toolkit is, we know that developers work by example. They prefer to get some working source code, get it into their machine, compile, and start to make changes, then to read the entire Bible about the APIs that we make available. So we provide examples in C#, C++, and Visual Basic, and we provide links to our SDKs, and that is what the toolkit team does. And we are having a lot of success convincing companies to do applications for the Kinect. But now let's dive a little bit into skeletal tracking, how we do this. Any questions before that? Okay? Okay. So the first thing that we do is, we need to calculate that. How to calculate that? So the goal is, we have this projector here, and we have a camera that is a little away from the projector. I will show later exactly what the camera is seeing, but you can imagine that there must be a mathematical way to calculate the depth based on this. Okay? I will show the mathematical way. At the high level, what we want is, we want to give you just 20 joints. So where is the head, where is the right knee, where is the left knee, so that you can make code that is just based on the joints. Oh, the hand moved from bottom to top and so on. You don't want to make software based on, oh, the pixel changed from here to there. That's what computer vision has to offer for you. So the way it is exposed to the developer is something like this. And even though you don't understand the entire source code and even the language here, which is C#, basically you start a Kinetic, you enable the device, you say, I want the skeleton data, and when the skeleton data is ready, call this method here, and please, Kinetic, start. So it is very simple, and when Kinetic has data, it sends to you, and you can just copy this data to your buffer and so on. That's all that is needed in terms of code. So literally 10 lines of code and you get the data. But let's not focus on this here. Let's focus on what we really do. So the first thing that we need to do is get depth. Any camera can give you the RGB data. The depth is where the secret really is nowadays, and you saw a lot of presentations already with applications of that. So how do you do this? So the thing that the device is doing is, there is a laser pointed at you, but luckily it is a laser that is spread through. So let's go again to our application here, and use that application that we have to use to explore the Kinect. So this application here will show you this, and I will ask it in the color stream to show you the infrared. So you are too far away, so I'll have to point at you here. I believe, okay, here it is. So because the pattern is kind of spreading. So basically what is happening here is, a pattern is being sent in infrared. It is infrared because most people like to watch, for example, TV or play games with the lights down. So infrared will still be visible there. So what is happening is, a signal is being sent here, and, oh, let's point that bit. That's probably fine. Okay, so the signal is being sent. And I can calculate that because basically when I come here, the pattern, if I know the pattern of points that is being sent, I know that as I move something in this area, what is happening? These points will be in different distance when seen by the camera. So, some geometry and some math, and I believe that most of you can resolve this problem. So it's left as an exercise, okay? So, basically this is how it is done, okay? The infrared is spreading a pattern. This pattern is totally diffuse, and basically, based on this pattern, we calculate that. So, let's go back and continue getting the information. So, after we got that, we can easily do a depth map. So, if I have a point in space and I know its color and I know its depth, it is possible that I can even show to you where this point is in space. So I will connect this application here to that other application, and I will show to you what is that the application is seeing in terms of color. Oh, sorry. I have to return color to the RGB string. So let me return color here to show the RGB data. Okay, cool. So then let's go back to that application. Okay, so that is the color, that is the depth as visualized. But here is the cool part. That is me and the depth projector. Okay? So basically, except for you, that I am projecting my points in 3D space. So this information is made available back to the application. And you can see some lines, for example, the device, when it is in the Xbox mode, which is the default mode, it cuts depth when I come closer to 80 centimeters. Okay? And when I can put it in what we call near mode, and it will give you the depth even when I'm 40 centimeters away. So, did you all get the idea of that view? Basically, I can then have this depth map being used as the basis for my segmentation, isn't it? The next thing that I need to do is background removal. I need to remove what is the player and what is the background. Okay? So, if you pay attention to the application when I am using it, you can see in that back window there that it is doing a segmentation all the time and creating large blocks of regions. Can someone help me here? Because it can do for 2 people at the same time. So see, it does the segmentation all the time. And if you saw the presentation this morning, segmentation is one of the hard parts, isn't it? But I have that information. So I can segment with a lot of confidence. So that's cool, isn't it? The segmentation problem that is typically the hardest problem becomes far simpler. And how can we do it? Well, you are experts in image processing, so you all know that we can do connected components. So we just really go through the depth data and connect the components that are at similar depth. Okay? Cool. So I have now what? I have this large box that I believe they are something. I still don't know what it is. This is called segmentation map. You can have, even for players that we don't provide you the skeleton, we can give you the segmentation map. Okay? I'm not going to details here because I'm taking a lot of time already. So, okay. Now we have a problem. You remember the presentation this morning? What is this problem? What is the problem? What? Parts. Fantastic. And that was not kind of rehearsed. He was not here for the rehearsal. So, yeah, people missed the rehearsal. It's fantastic. So, we need to map these two body parts. And that is the technology that you really need to learn if you want to have any future in computer science, which is machine learning. Basically, we have one of the best machine learning algorithms in the world right now. Because we sold 20 million of these devices, we know people are extremely happy. But what is the thing that you need to do any machine learning algorithm? What? Training data. He didn't come to the rehearsal, he's very good. The key thing it is, you need this thing that we call ground truth. Data that is annotated, that allows you to create the basis for your machine learning. And that is the big difference between industry and academic world. In the academic world, you can kind of come here and say, I tested my algorithm with 12 people, isn't it? I captured 12 people, I have 100 frames, and I tested. Okay? How many people do you think we test these things with? Tens of thousands. How many frames you think we have for ground truth? Millions. Millions of frames where someone is paid at $20 per hour to go and annotate. The hand is here, the arm is here, here. It's here. Millions of frames. We have people that train the taggers. These people are called the taggers. We have the taggers, we have the people that do quality control over the taggers, we have all those things. And then millions and millions of data points. Because whoever has any background in machine learning will tell you, the algorithm doesn't matter. What matters is the data. If you have the data, it will solve the algorithm problem. But if you don't have the data, it is a guess. So we have then to map this thing that is in front of the computer to a graph. A graph that is the graph of the structure of the body. This morning, for example, you heard about this thing of the difficulty of mapping the graph that comes from the input to the graph that is your known structure. We know that typically the hand is next to the arm, that is next to the body, that has a head, and some things like this, isn't it? So we have the graph that we are seeking for. Now we need to map the input to this. And that is where machine learning helps. We have this thing that it is these pixels in the 3D space, this point cloud, you probably heard of this. And we have a classification problem. Which body part, if that is a person, which body part this pixel belongs to? A lot of people try to solve this problem doing the segmentation of the body and then trying to simplify the graph matching. We tried something different. Indeed, the idea is from James Shotland, who is one of the co-authors of this paper, was published last year, kind of outlining the algorithm. What if we don't do the segmentation? What if we try for every single pixel to explore the features and try to use the structure that the body will have as part of this energy minimization equation that we are trying to solve? And that is where the algorithm, how the algorithm works. So let me show you a pre-recorded video because this is part of the paper and I want to really showcase what they did as part of the paper. And it is not showing here, let me see why. And if needed, we will have to go to the backup solution. that typically happens because of kinetic with two monitors. So let me close this and close this that you have seen already, so that we can focus on the video. Okay, so okay, so this is how the thing works. So the problem that we have is to do that classification. And for the Xbox, this had to be done in less than 5 milliseconds. So in the Xbox, of course, the algorithm was optimized for the Xbox. So this is the depth info. So it is very hard to do segmentation, isn't it? Infrared doesn't segment very well. So what is done, it is a classification, a very noisy classification map that indeed tries to classify every single pixel. Then you calculate the centroid for that mass that is classified according to the proper region. And then you have there the several views, and one is from the top of the body parts. Okay? So this is how the problem is solved. Basically, running this very efficient code that is classifying everything all the time. It will misclassify a few pixels. And because this is based on machine learning, it will sometimes not work. Because see, if you get into positions that people don't get at those positions normally, it will not work. Machine learning is perfect for classifying something that is within the input data, but when you are outside, it's not very good. So, back here. Okay? So, any questions so far? You still don't have the skeleton data. Why? Why you don't have the skeleton data? Even though you classified everything, even though you can have easily the center of gravity for a region, why is that I cannot give you this as a skeleton data? See, you don't make questions, I make them. Nobody?
Spatial relation between them.
There is a special relation. So basically that is exactly the thing. It is, you still have problems because machine learning will classify anything. Okay? If you put a dog in front of the sensor, it will probably classify the regions as something. But those don't match a human. A human has certain kind of limitations. Humans don't kind of, except for a few humans from humans don't do poses like this and things like that, and the leg is here and things like this. So you still need to filter out a certain kind of set of skeletons that they will come from the classifiers, but they don't look like good skeletons. Like sometimes the bones are kind of bent. It's like, wow, for the person to do that position, the bones have to kind of bend in a way that it is impossible. You know it is impossible. But the machine learning classified the parts, it found the center. The other thing is, the entire gaming industry is optimized for you to face your TV, isn't it? But then you have games like golf, and the thing doesn't play well. If you see the golf game for Kinetic, you have to play like this, looking at the TV. So the reality is, you still may have skeletons that are not really skeletons. So we have a lot of code to filter out those skeletons that, yeah, they don't look like skeletons. and then we finally return to you this output. And that is done. That is the past. What is that we are doing for the future? Before we go into questions and finish, kind of on time. There is a huge problem with the legs. Most people, they put the sensor in certain places, and then the legs are invisible. So you saw that even when I was doing the demo here, most of the time my legs were not visible. So the sensor, when it starts on the Xbox, I don't know how many people here have the Xbox and the Kinetic, when it starts, it goes through all angles, trying to find the best angle in which it can see the entire person. Of course, if you want to do this in the Windows software, you have to do it by yourself. But this problem is called crab legs. The legs keep dancing because the classifier keeps kind of changing its mind regarding where the foot is for each foot. So sometimes you even see this in Xbox games. There are Xbox games when sometimes you see, for example, tennis is common. You see the legs kind of dancing. And this problem is known as crab legs. We know about this problem. It's just that to solve it, you have to have a sensor that this sensor has a huge problem also. It was done for houses in the United States, where they have these huge houses. My house in the United States, I believe my apartment that I have in Belo Horizonte fits in the living room. So the thing is, it's done for the houses in the United States. In Europe, houses are smaller, even in Brazil. So the sensor is optimized for you to be 2 meters away from the sensor, playing these large TVs that Americans have. So yeah, it's not very good for Japan and other countries. So the sensor was not really thinking about this kind of angle, the angle for the vertical, and that introduces this problem. The other problem is smoothing. We are aware of this. We have some parameters that will smooth out the data for you, because the data can be a little jumpy if you just look at the raw data coming from the skeletal detector. Anything not in the training. Indeed, it is an interview question that I make to people that want to apply for our teams. And I ask, what do you think that happens if people misplace the sensor like this? What? Nothing. It doesn't work. Why would it just not work? What is that just not working with you? What?
The depth will be okay.
The depth would be okay, exactly. So why it is just not working? Skeletal tracking would not work. So I need to create a head here. Let me try to create a head. So sometimes I think this black thing that reflects. So sometimes I manage to make it see a skeleton. Anyway, So the thing it is, why? Because it tried to match, it found a match that, see, the joints are not so confident, and they are jumpy, isn't it? But it found it. Again, this is computer vision, people. State of the art. There's nothing better. If you have something better, you sell a lot. So, and it keeps seeing, see? It's, but I believe there is a person. So, really, it's seeing him, but see, his legs are not visible. So, it is just kind of jumpy. So, and that is a problem. The next big problem is this thing that we call mini-me's. Sometimes there are small regions, and it is very funny because sometimes the computer sees those things, and then you go there and you kind of, yeah, from the distance I could see a person there. It sees the persons that obviously are not there, but then you squint a little bit your eyes and, yeah, if it filtered out that mini-me, also probably a child there would not have been seen. It's very hard to solve this problem. Multiple devices. It is the top request for us right now. People want to connect 2 or 3 devices to the PC so that they can make games with 4 people, they can cover a larger area. And our skeletal tracking, because that was the way it came from the Xbox, can only work for 1 sensor. And the top reason is performance. I told you, it takes, of course, in the brand new machines, we have a machine in our lab where we connected 8 devices, run skeletal tracking for 8 devices, and it's fine. But not everybody has this machine. Many people don't have machines worth $25,000. Okay? So we have those machines for our testing, but we need to make it work for the typical machine. So we keep optimizing performance. Maybe if it is the only solution, we will go back to requiring a GPU, which by the way is a complaint from people. People that have GPUs complain, why don't you make these things on the GPU? I have this machine with the top graphics card that I decided to buy. It's not using this graphics card, is sitting there doing nothing. So, I hope what I have shown you basically is consistent with my conclusions at the beginning. So, it takes a lot to do software. You see, it is data typing, learning, machine learning, training a lot of data. We code very little. Very little new code is done for the project nowadays. What we really succeed is because we have a lot of people that know a lot of areas that are enabling the kinetic device to work on those areas, and developing software is far easier than developing software is far easier than developing software.